in terms of the previous one, right? So you know how to define your n tuples. Okay? And why do I need this? Well, because I want to speak about things like this. I want to speak about which I will be shortening to R3. I want to speak about n copies of this, which I will be shortening to Rn. Okay? So, what will be this? Well, this will be all those n tuples. That brings us to this part. Okay. That brings us to this first part of the. So the next part, I'll be speaking about functions. Do I continue or do you need a break? Okay. So, functions. The whole idea is to come in with a formalism, which the idea is same as this black box picture. So you have certain inputs and there is this strange black box which is called the function, does something. Okay? So you put in something over here, it churns out an output. Now, a little more closely, the idea is that this black box takes in an input and churns an output. That's fine. But taking an input from this side, it cannot churn more than one. But it could possibly take in two separate inputs and churn out the same thing. Okay? So for instance, x squared takes in 1 and returns me x1, takes in -1 and also returns me 1. Right? So two different inputs might churn out the same output, but starting from one input, that output must be unique. Okay? That output must be unique. There's no other way. Otherwise, this will break. Okay? So when we have to produce this kind of a thing, what are we demanding? So we have a set of inputs. This is usually called the domain. And we have a set of outputs. It is called the codomain.
Does the term range used doesn't apply here?
Yes, it applies. I'll tell you. Okay? Now, So it takes something from. So it takes something from the domain. God knows, does something strange inside that black box, churns it, produces a member of that output, of that codomain. Yeah? So how do I model this? I can think of, now having introduced pairs, I can think of, so suppose my input, so this is my domain, and B is my codomain. So these are two sets. Well, think. On the left-hand side, I have several inputs, results. I take one from here, the black box does something, gives me something over here. Okay? So why do I not take all pairs of things? The first coordinate coming from A and the second coordinate coming from B. Okay? So I look into these things. So that means I look into this big set. See how my notion of pairs came pretty handy over here. Okay? Now, what do I do? Remember, the inputs are coming from these A's. But these A's, so a particular such X is related to one and only one member of this output, right? Okay? So, why do I not? So, what is the function? Is a subset. Right? Subset. Where now I have to think a little more. The first thing is, every input must have an output. So, here are some conditions such that whenever I have an X in A, this implies that there exists a Y in B such that the pair XY is in F. Yeah? Right? For each of these inputs, I must have taken this, otherwise there is no point in considering, right? So I'm taking all those pairs which are going to give me that input output. But then the second one you said that, well, each input must give me one and only one output, right? So that means if XY and XY prime are both in F, then it must follow that Y is equal to Y prime. It's a way of saying that each input has one and only one output. So by XY belonging to F, I am saying the function F takes in input as X and produces output Y. That is what is my semantic, my meaning of saying. That's how I'm choosing that subset, right? Okay? So that was my underlying idea. By saying xy belongs to F, I wanted to say that black box which represents F takes the input as X and churns the unique output Y. That was my idea. Come in. So that's what I said. The second one says, if F takes the input X and produces two outputs, Y and Y prime, then in no way can they be different, they must be same.
Okay.
That's what I'm saying.
I thought you put the prime to the X, since the area is the
No, I said every input
in F.
Input is coming in the first column. Every input has one and only one output. So, my understanding of creating F was taking those pairs where the first coordinate is the input and the second coordinate is the output of. Right? So that was my understanding. So how do I represent it by conditions? The first condition says everything in this domain must have an output. So that is the first condition. Whenever X belongs to A, there exists a Y in B such that XY, that means XY in F. So as I said, thinking of XY in F to mean the black box representing F takes input X and produces output Y. Okay? So the first statement says every member from the domain, or which is the set of inputs, the black box takes it and produces the output.
Can Tom just mute there? We can hear what you're saying.
If you take maybe one variable from the input to the domain, you also get one.
You take an input, yes, the output must be unique.
One to one. Yes, not.
I didn't say one to one. I did say from the input side there is no two ways. But two different inputs might come to the same output. Right? Yes. It does, yeah, something like this. Two different inputs can go to the same output. But if you look from the input side, from the perspective of each input, when that goes in, there's only one way out. Right? So firstly, every input must give me an output. That's the first statement. Whenever I have an X in A, it implies that there exists a Y in B, so that the black box will output Y. Yeah.
I'm trying to test my understanding using the calculus to this thing. Say we have that function Y is equal to X squared.
Yes.
You can put negative 1, still get 1. You can put 1, still get 1. Yeah. So still a function.
Yes.
Yeah.
Now, using his idea, so I was asking, why don't you put the prime to the second set? Yes.
Okay, I'm coming to that second one.
Yes.
I'm coming to that.
Why?
Good. The first one says, you take anything, I'll get an output. The second one says, you take anything, I cannot get two outputs, I'll get only one output. So, what does this say? If xy and xy prime belongs to F, it means that X is the input, but F produces both y and y prime as output. But the condition says that it forces that they should be same, so that's the implication. Yeah? So that's that implication. So if that happens, then it must be that y is equal to y. Okay? Clear? So read this implication as, if this happens, then what will happen? Okay? Okay? So that's how we read it. Clear? So that Therefore, the prime has to be on the second, not on the first. Because if you did take on the first, if you take, say, xy and x prime y, you are telling me I have two inputs, x and x prime, giving me the same output. That I'm not, that's possible. Minus 1 and 1 by x squared goes to 1. So that I'm not excluding. But 1, if I take an input, the output is produced as unique, that is 1. That doesn't have any other option, right? That is what I'm trying to force. Okay? So that's the notion of a function. Okay? Firstly, we write, since this y is unique, we write often y is equal to fx. Okay? And call y the image of x under f. Okay? F is the function. F is the black box. Okay? So A is said to be the domain, B is said to be the codomain. The range of F is the set of all images okay? That's where your range comes in. Okay? It's precisely the set of all images. That's the subset of the codomain. Now, we often say when we, okay, now there is another thing which I will produce. So given any subset S of A and a subset T of B, so F of S, this is the collection of all the images when you take X from S. Okay? So what is F bracket S? That is the set of all images, but X is only taken from S, not from the whole of it. Okay? That image of S. It's called the image of S. Okay? And what is F? Now I shall write this bold. This minus 1 is bold. F, what is this? This is the collection of all x in A such that f of x belongs to T. So it's the set of all, well we say y is the image of x under f. We similarly say x is a pre-image of y under f. Okay? Pre-image. Remember, y, see there is a difference. Y is said to be the image because the image is unique. Right? But several x's, x prime could have the same image. Okay? So we say x is a pre-image of y. Okay? So y is the image of x and x is a pre-image of y. Okay? So this is f minus 1t. It's usually called the pre-images of T. This is the set of all pre-images of T. Pre-images or things whose image are coming from T. Okay? Let me draw. You see, let me take an example. And let me draw this. What is it? F of A. I will often draw this in this way. So, you see as if there is a kind of a right? This is my function. Okay? It's like those stocks and Pull&Grind kind of a picture, right? Yes?
Excuse me, sir.
Yes.
On the F, the first line statement there, the width is F, A, B, C, D. Then you have the arrow 1, 2, 3. Is that a like a notation?
Good. Yes, good. I didn't say it. Yes. Let me do it. Let me say it. I will write this fact. So this whole definition that I have written, I shall write this either by this symbol or by this symbol. Okay?
Okay.
And often over here, I will also write x going to fx. Okay? This is often said, or x maps to fx or so on.
Yeah.
Okay? Alright. So what I am saying here is f is a function whose domain is the set A, B, C, D. Codomain is the set 1, 2, 3. And I'm saying what are the images? FA and FC is 2, FB and FD is 3.
Okay.
Okay? Now,
So we can't just assume. So we can't just assume from that F domain A, B, C, D maps to 1, 2, 3. We can't just assume that there is a direct matching A1. So we have to rely on those definitions on the side. FA is equals to 2 FC.
Yes, remember what I meant by a function?
Yeah.
A function meant, so writing this is actually telling me that F is actually this subset.
Okay.
Yeah?
Yeah.
It is this subset. So that I have written in this so-called pictorial way as Fa is equal to 2 is equal to Fc, Fb is equal to 3 equal to Fd, which is actually this set theoretic thing. Okay? You see now, many times what we write is actually a pictorial description of something much more. Yeah. Yeah.
So is it possible to leave maybe one element unpaired
Yes?
in the domain?
No. No. Not in the domain.
So does it make...
That is exactly the first section. Whenever you have something in the domain, there is an output. So the domain cannot, good question, the domain cannot be left, but the codomain can be left.
Maybe you want the word they always exist.
Yeah, we mean, yes. Okay? Okay? So there exists is a much, much stronger statement.
Okay, if I may ask, what about
Yes, you're for?
MAT2611?
Okay.
If I may ask, so what about the one? What gives you the one in the function? There's nothing that has to do with one.
Nothing to do with one. Correct. So the codomain has many more things. It has, one doesn't have any pre-image.
Possibility.
Yes. So the range of F or I use this symbol IMF in my notes. This is therefore 2, 3. And 1 is not in the range. Okay? 1 is not in the range.
So the range is the output that appear to the domain.
Range is exactly the set of all output values. Yeah? Okay.
Yeah, I've noticed that you always use the IM.
Yes, IMF. Image. Yeah. So now, you see this picture tells me everything. This picture tells you what are the pre-images, what is what. Yeah, it's a very, very nice and suggestive picture. It is called the stock diagram. I like this picture very much. Stock diagram, because think of the pollen stalks. So these are the pollen grains, yeah? So that's why it's often called the stock diagram.
So you gave it the name.
No. It's well known.
Oh, okay.
It's well known. Possibly. Yeah, it's well known. It's called the stock diagram. Okay. Now let's see. So, the function f, so if you have a stock diagram in which everything is having a non-empty stock. Here I didn't draw the stock of 1 because it's empty. Okay? So if everything in the codomain has a non-empty stock, that means the range is equal to the codomain, right? Such functions are called surjective or onto. Okay? So,
Please repeat that again, sir.
yes, I will. So, given this function, we say that f is surjective. Or another word which is more familiarly used for you is onto. F is onto if the image of f, that means the range, is same as C. What does it mean? It means that every element B has a non-empty stock. So what is the stock? Let me again put, so this set is the stock of 3. That means it is the set of all 3 images of singleton 3, which we also write like this. Okay? So this is the stock of 3, this is the stock of 2, and the stock of 1 is not written, is not shown, so it means this is the empty set. The set of 3 images. So that means when every element of the codomain has a free image, that's when it is surjective. So everything has a stock. Okay? And when the stocks are singletons, so F is injective. I also say 1-to-1. You also say into. If and only if. Or if and only if this condition is true, that fx is equal to fx prime implies so that means, remember, fx is the output for x. So when from 2 places you get the same output, it forces that the inputs are same. Okay? On the stock diagram level, it looks like this. So I'm just drawing so the stock diagram level looks like this. Right?
Yeah.
Every stock is a line.
And in that y equal to an f squared example, you start limiting your domain from
Yes.
0 to
Correct.
positive number, no negative number.
Yes. Yes. So that is correct. Okay? So this is injective. Okay? So it's saying that every image has a unique pre-image. Okay? So in other words, it means every image or let me see if make this line, no, it doesn't. We wanted to make this line very thin. Okay, bijective or 2-1 correspondence. If and only if it is both see, example, the notion of an injection. Injection is exactly the name of that word. It just pushes this set inside this, right? It just pushes it inside the bigger one, right? It's some kind of an abstract way to say that, well, any more elegantly that, right? You're just pushing it here. Yeah? Things are just, whatever. Things are just getting pushed. But here is a nice, but surjection is actually some kind of non-unique labeling. So here is have you gone to a sushi shop? No. Everybody? Okay. So here is the deal. You sushi shop, rotating table with several kinds of fish rotating in front of you. You have to take, so they are, but then if you start observing, you will see that, okay, there are fishes kept over there, but some come in yellow plates, some come in green plates, some come in violet plates, so there are several colors, 4 or 5 colors of plates. Okay, then if you are curious, then you start, we'll be starting to do something else, but suppose you now take some dishes, okay, and you are now full, and you ask the waiter for the bill. Strangely, the waiter takes those finished dishes, okay, so there are 3 yellows, 2 violets, 4 pinks, comes back with a number. Okay? So what is he doing? What is he doing? Well, here is a typical example of a surjection. So salmon, say, and then rock cod, and so on. These are kept to violet. And there are a few others taken to blue. So this is the set of all the fish dishes. This is the set of colors. It's a surjection here. And then there is a bijection. Prices.
So I suppose, does it mean that you suppose you have surjective first, then injective?
Yeah, over here, yes, over here.
Does it follow certain pattern? Does it follow that certain pattern?
Yes, in general also we have that. I'll come to that. Okay, but so you see what is the surjection doing? So therefore, the waiter didn't need to know what you ate, whether it's rock cod or whatever. Those are all clubbed under pink. Okay? Salmon and etc. clubbed under violet. So it's enough to know how many violet plates do you have. That's it. Okay? So violet, and so you see, so surjection means a kind of a relabeling. You see? Your salmon and etc., they are relabeled to the waiter as violet. Okay? So, it is some kind of a relabeling. That is what a surjection is. And what is a bijection? Since it's a surjection, it's a relabeling, but it's a faithful relabeling. Why faithful? Everything has a label. Okay? But faithful means two things don't have the same limit. Yeah? So faithful that is the bijection. Faithful, you understand, I used it in usual everyday terms, right? So it's a faithful relabeling, so that's the bijection. That's the picture of a bijection. So whenever you see something like this, this means this, and therefore this means this. Whenever there is a back and forth kind of a thing happening between two different kinds of entities, you're actually speaking in terms of a bijection. Okay? Whenever you're saying, this, such and such things say this, you're thinking in terms of a surjection. Okay? So that's the whole idea. That's how you should see in life also. Whenever you can see, this is a surjection, this is a bijection. Okay? So that's the whole idea behind this. Clear? What you're saying is, I'm coming to it, and that is, so now, before I come to that thing, I have two functions, and when should I say they are safe? The equality of two functions. Obviously, as I explained, it must mean that the set of inputs must be same, the set of outputs must be same, okay? And the rules must also be the same. Whatever I input here, then only those two black boxes are set, right? So that means there are three conditions. So that means F must be equal to G as sets. Right? As sets. So this means A must be equal to C. That means the domains must be the same. The codomains must be the same. And for each x in A, which is equal to C, Fx must also be equal to G. Right? That means the outputs given by the two must be the same. Okay? So that's the equality of two functions. Okay? Alright. There is another notion of a function which is quite important, which is the notion of a composite.